Hey, what's up, guys? Okay, so today I want to talk about is Hurwitz theorem, and this theorem is interesting because I mean the proof is really interesting, and I want to share with you guys. Also, this is Hurwitz theorem. So that A be a constant satisfied from 0 to square root 5. If alpha is rational, there is an infinite many rational number PQ satisfied alpha minus p divided by q less than 1 divided by a q squared. So example is, and 1 over square root 5 divided by 2 will shows that square root of 5 is the best possible upper bound in A. Okay, so remember there's a theorem that which called Dirichlet. So Dirichlet's theorem tells you that alpha minus p divided by q less than 1 over q squared has infinite solution. Has infinite pq solution where there are they should be equal prime. Otherwise, that is trivial. Okay. No. Yeah. They should be. Yeah, they should be equal prime. Okay. And there are infinite solutions. So so one might ask that how can I do this, right? Maybe I can like shrink more, or I can maybe put 100 here, 200 here to make it stronger, right? But which this theorem tell you that the square root of 5 is the best. Okay, so yeah, so basically the square root of 5 is the best constant that you can get. Okay, so for example, if you make A to be larger than square root of 5, then there will be finite solution. Okay, so you can find some strange irrational number such that always have finite solution, and then this strange number is 1 plus square root of 5 divided by 2. Okay, and if you don't know how to prove the Dirichlet theorem, then you can check out my video. I will post link below. Okay, so let's go through a proof. The proof is interesting. Use things broadcast series. So let me just write down and tell me what how to do this. So imagine that we are trying to write PQ where Q greater than 0. I denoted this PQ pair to be P divided by Q. And notice that when Q equals 0, I just define it to be nonsense. Okay. But I will still define, I will still use it. So B0 I define to be 0, 1 and 1, 0. Okay, so you can feel 1 divided by 0 is a nonsense number, and this number will correspond to 0. And the B1, then I just define to be 1 divided by 1, 1 divided by 1. And the middle, the numerator, will define to be the median, so or the average, so 0 and 1 average, which is, oh sorry, 0 and 1 sum, so it's 1, and the 1 and 0, which is 1. Okay, so this 1 just the left and the right, the sum of the left and right, and the 1 just sum of the left and right, and I can divide B2. So 0, 1, 1, 1, and the 1, 0, and then for middle one, I get 1, I get 2. I get 2, I get 1. Okay, so you can view B2 has 4 numbers, 0, half, 1, and 2. Okay, and then you can define B3, which is 0, 1. Then we just write out previous 1, 1, 2, 1, 1, 0. And then for this one, you get 1 divided by 3, you get 3, 2. And then you get 3, 2. You get 3, 1. Okay. So you just keep going. Okay, you can define B4, keep going. Yeah, so I will not keep writing, but you can just keep writing. And there is a fact that I will not prove here, but it's easy to check. Is that if you have A divided by B and C divided by D, there are 8 adjacent in this broadcast series. Then you always have, then we always have. So there are 8 adjacent. For example, these two are adjacent, these two are adjacent. If they are adjacent to each other, then C minus D minus A divided by B, C divided by D minus A divided by D will be 1 divided by BD. For example, if you take this, you get 2 minus 3 divided by 2, which is 1 divided by 2, right? So it's, you can see it's 1 and 2 times become 2. Okay, so it's amazing that we can start to prove this theorem. Okay. So before we prove it, let me just quickly say something important. Okay, so I will define phi to be 1 plus square root of 5, and the phi bar to be 1 minus square root of 5 divided by 2. Okay. Okay, and notice that okay, so notice that if let's looking at, so there is a simple lemma. So this lemma tells you that if I define x to be b divided by d, then and I know that x greater than negative phi bar and phi. Okay. And what? And also like 1 divided by x is less than phi and negative phi bar. Okay, so you can check this. So if this is true, right? If x is greater than phi bar, negative phi bar, then you can just, by the way, right? So negative phi bar is greater than 0, right? So this tells you that 1 divided by x is less than negative phi bar. And notice that the negative phi bar will always be just simple. Negative phi bar will be phi minus 1. Okay. Okay, so what I'm just saying that what I want to say is the following. So I want to say that let's see, if x satisfies these two, then if b squared minus bd square root 5 plus d squared less than 0. Okay. So proof is very simple. Let's see. So maybe for this direction, right, I can just write b squared divided by d squared minus b divided by d square root 5 and plus 1. Then I get x squared minus x square root 5 plus 1, then 0. Then I will get this, right? I will get this. And because the roots is just phi and phi bar. And also I can also write d squared minus b squared minus d divided by b square root 5 plus 1 less than 0. Then I will get the x minus 2 plus x negative square root 5 plus 1 less than 0. So I can get this one. Okay. So that means this direction is simple. And these directions, this direction which should also be simple. You can check by yourself, right? Because yeah, basically it's the same, right? Because if you write x equals to b divided by d, then you can write b divided by d minus phi and b divided by d plus phi bar will be less than 0. And then you collect it, then you can get this equation. So both basically these two give you the same equation. Okay, so this is just fact. Okay, and another lemma. I think this is lemma 2. Lemma 2 tell you that if somebody give you BD, right? If BD, which are all positive integer, satisfy the, so they are all positive. Yeah, so they're all positive. Okay, let's say satisfy the b squared minus bd square root 5 plus d squared less than 0. Then one can then if you add the d, right? If you add the d, you get b plus d squared minus b plus d square root 5 plus d squared will be greater than 0. And also if you do another direction, which you get b d plus b square root 5 plus d plus b squared will greater than 0. Okay. Okay, so you can, this is interesting, you can try to prove it. But basically the idea is very simple. We just using the previous lemma, right? So if I consider x to be b divided by d, and things satisfy this, right? This tell me that x will less than negative phi bar and phi, and x is b divided by d. Now I can simply say that if x plus 1 will be what? Will be b plus d divided by d will greater than negative phi bar, right? So it will be 1 minus phi bar, which is phi, as I say. Okay, so this means that b plus d divided by d is greater than phi. So if you have this, then you can collect it, right? You can write b plus d divided by d minus phi, and b plus d divided by d minus phi bar, which is greater than 0. And you collect it, then you can get this term. Okay, so the same reason you can get this plus phi bar, and you can get these terms. If you flip it, right, you can consider 1 over x, which is d divided by b, and you're using the same proof. Okay, so we have these two weird lemma. Now we can prove the results. Okay, so in this case, right, I can assume, right, by the reverse, right, I should assume this irrational number. So I want to prove that basically I want to prove the following. I want to prove that I can always, if I can restrict alpha to be greater than 0, all right, just without loss of generosity. So I want to say that there is an infinite PQ such that alpha minus p divided by q is less than 1 over square root of 5 of q squared. Right, so I want to say that this square root of 5 q squared. I mean, at least I can find infinity of this PQ. Okay, so proof is very simple. Okay, so the proof is notice, right? So this, you can see this Broca series can go to infinity, right? So since alpha is irrational, so you can always find some adjacent Broca series, right? Two number which is adjacent to it. Okay. So case one, right? Case one is that b squared minus b d square root of 5 plus d squared is less than 0. Okay. Suppose this is true. Okay. You can this is right. It's either greater than 0 or less than 0, right? But let's suppose let's maybe do the first case. Let's suppose it's larger than 0. Okay. Okay. Then what? Then my claim is that alpha minus a divided by b is less than 1 over b squared divided by 5, or c divided by d minus alpha is less than 1 over d squared divided by square root 5. But basically, I want to say that one of these must be true. Okay, why this is true? Proof is very simple, right? Suppose not. Suppose not means that these two are false, right? These two are false. That means that if you add, you can write c minus divided by d minus a divided by b to you writing as c divided by d minus alpha plus alpha minus a divided by b, or less than 1 over d squared plus 5 and 1 over b squared divided by 5. And using the property as I said, right, this is always b1 divided by bd. So you get 1 divided by bd less than 1 divided by square root of d squared 5 and the b squared 5. And if you get it, then you can write, you get b squared. You can get what? You can get b squared and d squared minus square root of 5 bd. Let's see. Oh, sorry. Because you assume that these two are all false, right? So this should be greater than 0. Okay. Because I assume that these two are all false, so these are greater than 0. Then I can get this, right? I get this. Okay, but this contradicts with our assumption, right? So this means that this must be false. So one of it must be true. Okay. So in this case, that we finish the proof, right? Because now I prove that one of it must be true, right? So I prove that a divided by b, c divided by d for some particular alpha. This one of it must be our candidates, right? So these two, one of it must be good approximation. One of it must satisfy 1 over less than b squared divided for b 1 over b squared divided 1 divided by b squared square root of 5, the 1 over d squared square root of 5. Okay, but you can also find the median, right? You can, after this step, then you can find the mediate, right? So, or the median, which is a plus c, b plus d. And then the same reason, right? One of it must be the candidate. Okay, and you might think that, oh, maybe it's still this one, but it's still fine, right? You can always find another one, right? So you can always, if you find this one is here, then one of it must be true. So you will keep going, right? So this will give you infinite solution of PQ. And alpha is irrational, right? So there's always a solution. Okay, so this is our proof. Okay, so case 2, right? Case 2. Okay, so maybe at some Bn level that you just, oh, I find alpha is like greater than a divided by b, and then it's c divided by d, but what? But b squared plus d squared minus bd is in d square root of 5 is less than 0. Okay. Then what's going on? Okay. But okay, if this is true, so if this is true, then I cannot get the previous results, right? Because maybe both are not good. But in the next level, like bn plus 1 level, then I will consider which number. So I may consider a divided by b, and a plus c, b plus d. Maybe alpha is here, or a plus c, b plus d, c divided by d, and alpha is here. So either one of it is true, right? But there is a lemma 2. Lemma 2 say that if this is true, then if I add it, this, then this will be greater than 0. So that means that what? That means that this one, this one must satisfy the results, right? Must have b squared plus this one, right? This one must have the results, right? Because we always have b plus d squared plus d squared minus b plus d squared root of 5 greater than 0. So that means that if you cannot find a solution at bn level, then you go to the next level, bn plus 1 level, by this lemma 2, you must find a solution, right? Because now b and b plus d and b plus d and d must satisfy one of it must satisfy the results. So that means that you prove the following. So basically we have shown one of it must be true. Okay, so either alpha minus a divided by d, b is less than 1 over b squared square root of 5, or alpha minus a plus c, the middle one, b plus d, is less than 1 over square root of 5, b plus d squared, or alpha minus c divided by d is less than 1 over d squared divided by 5. Okay, so one of it must be true, which proves the results, right? Because you can keep always find using the median, and then you keep going median, and you get infinite solution. Okay, so since we only prove alpha is greater than 0, but alpha is less than 0, you can just flip it. Okay, so the theorem that I want to say is that square root of 5 is the best. So that means that if you pick a number which is greater than square root of 5, then you, for some particular weird number, you can always find an infinite. You find an infinite solution. You can only find a finite solution. Well, pretty simple. You consider phi to be the golden ratio, and the Fn to be the Fibonacci, n Fibonacci, and so f0 is 0, and f1 is 1. Sorry. Yeah, so f0 is 0, f1 is 1, and fn plus 2 is n plus 1 plus n. Okay, and we all know that fn is phi n minus phi bar n 1 over square root of 5. Okay, so if you don't know how to prove it, you can use generating function or check out my other videos. And also fn phi minus fn plus 1 is equals to phi bar n, which is minus 1 to the n divided by phi n. Okay, so these are just some common equation that you just easy to prove for yourself. Okay, now you can check that phi minus phi n fn divided by 1 divided by fn will be 1 divided by square root of 5. Direct computation, you get fn plus phi bar n. Okay, so you notice that phi bar n is always greater than 0. Or phi bar is greater than 0. Okay. But it's less than 1. Okay, so that means that what? That means that if you pick up your constant, right, greater than square root of 5, then for large enough n, then you get square root of 5 fn phi bar n, right? So this term can be arbitrarily large. Can be arbitrarily large. I think so. Let's see how I can explain this. Okay, so what I'm saying is that okay, so let me just write down. So you get phi minus fn plus 1. Fn is that we're 1 over square root of 5. Fn plus phi bar n. Okay. So I can write 1 divided by square root of 5 fn squared and square root fn 5 bar n. Okay. So if I want to say these guys less than, let's say I want to say these guys less than 1 over, like, if I want to write 5 divided by p, 5 minus p divided by q less than 1 over, let's say, q squared, and the square root of 5 plus epsilon. Let's say I choose a bound greater than epsilon. Okay, so I will say this is true. I will say, oh, this is fn squared, square root of 5 plus epsilon. Okay. But this will give me something, right? This will give me I can so if these two are true, right, then I get the square root of 5 plus epsilon less than fn squared, square root of 5 plus epsilon less than square root of 5 fn squared plus square root of 5 fn 5 bar n. Okay, so let me just kill one fn. Kill one fn. Okay. Then I will get what? Then I will get the epsilon fn, because square root of 5 fn cancel, will less than square root of 5 bar n. Okay. And so obviously that these epsilon, right? If you fix epsilon to be a fixed number, then when n goes large enough, then this equation cannot be satisfied, because when n goes to large enough, this fn will always go to infinity, right? But this 5 bar n will goes to 0. So that means that the left hand side can grows and the right hand side will be goes to 0. So that means that if you fix epsilon to be larger than square root of 5, then this golden ratio always have finite solution, right? Because you only have finite n such that this equation is true. Okay, so you have only finite solutions for a greater than square root of 5. Okay, so this is the proof of this very interesting Hurwitz theorem, and I will post the reference below. I think its proof is very interesting, very easy, and amazing. Okay, see you guys next videos.